This video goes through the answers to the Exploring the Rational Functions worksheet starting with number 1. The climbing the wall problem, the introductory problem, is a separate video. I want you to watch this until I say to stop, and then stop and continue working on the video on your own, and then you can restart it. The first page is pretty basic stuff. We see here the graph. Basically, the only thing I need to tell you about this is if you had any trouble with dividing by a fraction without using your calculator, hopefully you were able to do this in your head. When you divide 1 by -1/2, it's the same as multiplying 1 times the reciprocal of -1/2, which gives you -2. So notice that as x, with bigger x, we get smaller y, and with smaller y, we get bigger x, and vice versa. But when x is 0, we have an undefined value, so we do end up with asymptotes. And then when x gets really, really, really big, we end up with y getting close to 0. As you see by these additional points, when x is really big, then we get y becoming very small. When y gets big, what happens to y is x gets very close to 0. That's where we have our vertical asymptote. Y is either going to -infinity or +infinity. When x gets really big, then we have y leveling off to 0, getting closer and closer to 0. Because basically what happens is if we have 1 over infinity, in math that becomes 0, 1 over infinity, because you're saying 1 over an infinitely big number is for all intents and purposes 0. More of a concept than an actual computation, but that's something you have to think about. 1 over infinity. So 1 over a very large number gets close to 0. Never quite equaling 0, though, so this is an asymptote. Notice that as x gets really large in the positive direction, y remains positive but very close to 0. When x gets really large in the negative direction, y gets very close to 0 but remains negative, and that's our horizontal asymptote. Now number 3, 4, and 5 talk about what happens then if we take that basic parent function, y equals 1 over x, and we start changing some things. So the first thing is we're going to change the 1 in the numerator to another number, 2, 4, -1, -4. So what happens first of all as a gets bigger? As a gets bigger, either positive or negative, it gets bigger. You notice that the curves, the distinctive curves, these curves right here, are farther now from the origin than they used to be. If you know when a becomes negative, then you notice we switch from having the curves in quadrants 1 and 3 to having the curves in quadrants 2 and 4. The horizontal and vertical asymptotes, though, still remain on the x and y axis. But when we move on to the next problem, you'll see that the asymptotes start to change. If you look at number 4, adding something outside the function, if you remember from way back when we did our translations and rotations and dilations and so forth, when we change something outside the function, it affects the y value. So the y value would be affected by the horizontal asymptote. So either the horizontal asymptote is moving up or down. When we subtract, it moves down. When we add, it moves up, because anything outside the function does what we expect it to do. It behaves in a normal manner. Now, if we add or subtract inside the function, in other words, we subtract or add something to x first and then take 1 divided by that quantity, it acts in the manner opposite to what we expect. So if we subtract 2 from x, it actually shifts the vertical asymptote to the right 2. When we add, it shifts it to the left. Now let's think about that. Realize that when x is 2, that makes the denominator equal to 0. So when x is 2, that is when y does not exist. And when y does not exist, we draw a vertical asymptote to indicate there's a gap. There is no possible y value on that vertical line. Then same thing with here. And then number 6 was, could you apply what you learned in number 4 and 5? So you should notice that there is a vertical asymptote at -5, because that makes the denominator equal to 0, and a horizontal asymptote at 2. Now, pause the video or turn it off right now. Probably pausing it would be better. Go back and work on the next section, number 7a through a, b, c, d. Now, those are some of the tougher problems, so if you don't know what to do, then I will work the first. You can turn the video back on. I'll work through the first problem with you and show you how to do it, and then you can go ahead and continue on from there. Actually, I decided to do problem number 2 with you, or B, because I thought that might be a little bit more applicable. It has 2 different asymptotes rather than just one change, so it'd be a little better for me to do as an example problem. Okay, you have numbers A, B, and C you're trying to find in this form of the function, and you know that B and C hopefully are determined by the asymptote. So let's start with that. If I were to draw an asymptote, it appears that we have an asymptote here. 1, 2, 3, 4. This is at x equals 4. And we appear to have another asymptote. Actually, I was wrong. This doesn't have 2 different ones, but that's all right. Well, it'll still be the same basic idea. And we have an asymptote at y equals 0. So I would say that B is going to be 4, and C is going to be 0. So this is what I have so far. I have f of x is equal to a over x minus 4, because 4 would make the make y undefined, so that's where my vertical asymptote is, and plus 0. So if this asymptote was somewhere other than the x-axis, then I would have a different number here. The question is, how do I find a? To find a, you need to locate one other specific point that's on the graph. So look for a place where the graph crosses through the grid lines at an intersection point. And I'm just going to say, just assume that that is a point on the graph. So I see an intersection point right here. This is the point, looks like 3, 1. So what I can do, I think it's 3, oh no, it's not 3, 1. I was just counting from the asymptote. Sorry about that. Half point for me. 1, 2, 3, 4, 5, 6, 7. This is the point 7, 1. So what I'm going to do is plug 7 in for x and 1 in for y and solve for a. So I can say 1 is equal to a over 7 minus 4, or a over 3. So if 1 is equal to a divided by 3, I can multiply both sides by 3, so 3 is equal to a. So now I know what a is. So I can write my equation, f of x is equal to 3 divided by x minus 4 plus 0. You don't really need the plus 0, but if you want to put it exactly in this form, then you could do that. Okay, at this point I want you to pause the video and I want you to do the other 3 by yourself and then turn it back on to check your answers. Okay, you can look here. A should be f of x equals 1 over x plus 4. I use the specific point 1, 5. If you put in 5 for x, if you put in 1 for x, then you'd have to, that would be 1 plus what equals 5, and so y would have to be, or I'm not saying this very well. If I put in 1 for x, then my c value here would have to be 4 in order to get 5. C should be negative 5 over the quantity x plus 4. Once again, there is no y-intercept change, or the horizontal intercept doesn't change. I use the point 1, negative 1, and plugged it into the function. So negative 1 is equal to a over 1 plus 4, and solved that for a and got negative 5 for a. For D, both asymptotes change here. So I have an asymptote at negative 4, so this would be x plus 4 down here. I have an asymptote at negative 3, so this is minus 3 for the c value. To find a, I picked a point. There was probably other points you could have picked. Looks like you could have also picked negative 2, negative 4 as a point. I used negative 6, negative 2, plugged in negative 6 for x, negative 2 for y, and solved it for a. And here's the rest of my work down here. Got 1 equals a over negative 2, so a is negative 2. And you should have also realized a is negative both in C and D, because the way the curves are, the curves are on the upper right and lower left instead of the upper left and lower right instead of the upper right and lower left. So that's how you can tell that would be negative. I'm going to talk through number 8 because I'm figuring that a number of you probably had trouble with this. I'm hoping you don't, but maybe you did. To start, since I want to add these 2 fractions together, I'm going to write 2 as 2 over 1. And then I need to get common denominators. So the common denominator is x plus 5. So I'm going to multiply 2 over 1 times x plus 5 over x plus 5. That would give me 1 over x plus 5 plus the quantity 2x plus 10. I'm multiplying the 2 times the x plus 5 all over x plus 5. Now that I have common denominators, I can add the numerator, so I end up with 2x plus 11 over x plus 5. So if you were to graph 2x plus 11 and over x plus 5 and 1 over x plus 5 plus 2, it's exactly the same graph. Now let's go on to number 9 and do this one together. Rewrite the rational function. So now I want to go from I want to go from a single fraction and then put it in the form a over x minus b plus c. Oops. So what I need to do here is to divide the numerator by the denominator. And this seems really odd because they're both an x to the first, but because I have a larger coefficient in the numerator, this actually works. I'm going to use synthetic division. So basically, I'm going to rewrite f of x is equal to negative 5x plus 7 divided by x minus 2. Since I'm dividing by x minus 2, I put a 2 here. What goes in the top is negative 5 and 7. I bring down the negative 5. 2 times negative 5 is negative 10. I add that and I get negative 3. That's my remainder. This is a constant. So basically what I've just said is that the answer to this is negative 5 remainder 3. Now how do I write a remainder as in sort of a mixed number form? So let's just recall. So I'm going to get my little thinking man over here. Little thinking man. I guess it could be a thinking woman. I'll put a skirt on. There we go. Thinking woman. And I'm thinking, let's divide 10 divided by 3. If I divide 10 divided by 3, I get 3 remainder 1. Well, how do I write that? I write that as 3 and 1/3. When I write 3 and 1/3, I'm actually writing 3 plus 1/3. Okay, does that make sense? So here's my little thinking block all over here. So what I'm doing when I have a remainder 3, notice that I took, here's the answer I get, the whole number answer I get, and then 1 divided by what goes in the denominator here is what I divided by. Okay, so 1/3. I divided by 3, so I get 3 whole groups of 3 and then 1 out of 3 for that last part. So what I'm going to do here is rewrite this as negative 5 plus 3 over, and what did I divide by? X minus 2. So there we go. F of x is equal to 3 over x minus 2 minus 5. So now I've written it back in the other form. Now I want to look at these graphs. I want to look at a couple things. You've got some extra space on the bottom here. Draw a little line. I want to examine the two forms of the graph and what they tell you about the asymptotes, because we know what this particular form, the a over x minus b plus c, tells us. But what does the other form tell us? So let's look at the two pairs of things we got. In the first section we have f of x equals 1 over x plus 5 plus 2. F of x equals 1 over x plus 5 plus 2. And that's equivalent to 2x plus 11 over x plus 5. Now here we found out that we have a horizontal asymptote at y equals 2, and we have a vertical asymptote at x equals negative 5. So how could we figure that out from this form of the equation? Well, notice, well, actually I'm going to hold off to say that for just a second. I'm going to put the other one down and then we'll kind of compare these. The second one, we have f of x is equal to 3 over x minus 2 minus 5, and that's also equivalent. Humor me a bit, that looks really sloppy. I'm going to rewrite that. 3 over x minus 2 minus 5, and that's equivalent to negative 5x plus 7 over x minus 2. 5x minus, plus 7 over x minus 2. So I want you to notice here, let's start with the vertical asymptote. let me do this again over here. Horizontal, we have y equals -5. Vertical, we have x equals 2. So let's take a look and see, how do you tell from this form of the equation what the vertical asymptote is? Now, that's the very same. Notice we have an x plus 5 here. We're going to get an undefined value when x equals -5. Here, we're going to get undefined value when x equals -5. So it's very easy to tell the vertical asymptote from either form. Either way, we're going to get the denominator equal to 0. Here we have an x minus 2 in the denominator. Here we have an x minus 2 in the denominator. Vertical asymptote, obviously going to have to be 2, either form of the equation. But how about the horizontal? How do I find the horizontal asymptote when the equation is in this form? Well, I want you to notice where this number shows up. This constant shows up as the coefficient. If I were to take 2x and divide it by x, I would just get 2. Here, if I were to take -5x and divide it by 2, I would just get -5. Let's think about logically, if I were to put an extremely large number in for x. So sometimes I call that a VBN, very big number. If I were to put a very big number in for x, basically we're saying what happens if x goes to infinity. But let's say 1 million. Let's say I put 1 million in for x. I would have 2 million plus 11 over 1 million plus 5. Is the plus 11 and plus 5 going to make a whole lot of difference when I'm talking about 2 million? No. What if it was 2 billion? 2 billion and 11, 1 billion and 5. 2 billion and 11 divided by 1 billion and 5 is pretty close to just 2 billion divided by 1 billion, so we end up leveling off at 2. Not exactly 2, but getting very close to 2. So y gets very close to 2 when x is really big. Same thing over here. I put x, a very large number, in for x, like 1 billion. The plus 7 and the minus 2 isn't going to change the size of that number very much. So when I put -5 billion plus 7 divided by a billion minus 2, it's pretty much going to level off to -5. So y is getting really, really close to -5. So if we take the highest degree term and just reduce it, we're going to figure out what happens with that horizontal asymptote. So that's a little preview of coming attractions, number 9, for what we're going to do in our next class session and when we talk about how to graph rational functions.